Hey guys, Vincent here, and in this video I want to address a question that I received recently on one of my videos regarding distillation columns, and it is an excellent question because in many ways it captures why I failed to really understand chemical engineering before I got into this field as deeply as I did in my undergrad. And the question was, why can't we control the temperature between two plates within our distillation column? And the direct answer to this question is that these plate temperatures that you have as you're looking at your distillation column are outputs. They are not inputs. They are outputs of essentially a black box that we have at our disposal as chemical engineers. And I get very philosophical sometimes when I'm thinking about these things because I don't necessarily like jumping deep down into the math or working through a problem statement per se always. Sometimes I just like taking a step back and thinking about, what are we working with here and what can we control and what can't we control and how do we do the best we can with what we have available to us. And so when we think about distillation, we basically have a black box. We have some feed going into this black box. We have a distillate coming out of this box, and we have a bottom stream coming out of this box. And so the questions that are intuitively answered by you as a chemical engineer are like, what can you control in this box? And the answer is within this box, your distillation column, you can control how much feed goes into your column. You can also control how much energy you supply into your reboiler at the bottom of that column that supplies the energy that actually generates that vapor phase in the first place within your distillation column. You can also control how much energy you take out of the top of it, which is called the condenser duty. So, do you really want to chill it down, or do you not really want to add any or take away any energy from your system at your top plate? You can control your reflux ratio, which is how much of your distillate you direct back down your tray. And then you can also control the number of trays that you decide to put into your distillation column. And uh, that's pretty much all we can do. And at the surface, when you're jumping into it and you're new to engineering and you're wanting to learn more about, well, let's change the temperature between tray 2 and tray 3, and then we'll have really good separation and have really high purity product. And the sad truth is that we don't really control these things. They're vapor liquid equilibrias that are reached at each tray in theory. And do we really even reach these uh, equilibriums? The answer is no, because it would take infinite amount of time to get there. So it's a very imperfect science. And engineering is not science. Because in science, I think of things like mathematics, where you can definitively prove that 2 plus 2 equals 4 without a shadow of a doubt. But in engineering, there are so many unknowns and so many variables that we simply cannot control that it's beyond our control many times, or it's, we can't do anything about it. So what we have to do is we have to fall back on what we can control. We have to look at what is the real world performance of the system, think about what is going on at each tray. And one of my favorite classes that I did only as a senior uh, in my chemical engineering program was we actually ran a distillation column. And I wish we did that a lot sooner, but I know that you won't really understand or appreciate the beauty of what's going on until you've learned the background behind it. But the gist of it is that, you can stick a temperature probe into each one of your trays and figure out what is the temperature of that tray of your solution. You can figure out what is the concentration of your species of interest in that tray by taking a syringe and pulling up a few microliters of your solution and sticking it into a gas chromatographer. But that's really all you can do. All you can do is just measure this stuff. And so the tuning knobs that you have available to you are just things like how much energy do you put in and what is your flow rate, and that's kind of it. And so I really like these types of questions. It makes me think, and it also makes me be very clear in how, what can you really do in practice as an engineer, and what are we physically able to do. And I really appreciate these types of questions. If you have more questions regarding engineering, kind of philosophical sides of things, these are my favorite things to talk about. But yeah, I hope this adds some insight into the black box that is distillation. And for so many people, for so many engineers, while you're going through your undergrad, distillation is this huge black box. It just doesn't really make any sense. And you have to go through thermodynamics to learn about vapor liquid equilibriums. You have to go through mass transport to begin to understand why a lot of the things that we hope we'll get to 100% equilibrium. Like, do we really reach equilibrium? The answer is, of course not. You might get 70% of the way there on a good day. And so, what does that mean? How does that affect the number of trays you're going to need in this column? And so, yeah, these are all really good questions. And I hope this kind of inspires some of you to think about what is going on here behind the scenes inside of these, towers that you drive past going through the Richmond refinery in the Bay Area. And it's really cool stuff. And I hope this is useful or exciting for some of you who are into chemical engineering like I am. And thank you for watching.